welcome to this presentation. It's a part 1 of 2. I want to talk about the new anisotropic inversion approaches in the JSON software. And this first part is about the method which is a bit unorthodox, so we need to explain that a bit. And the second part is where I talk about some examples. So just before we start, I would like to emphasize that this is not about intercept and gradient analysis. And intercept and gradient analysis tells you something about layer boundaries. So you're looking at reflectivity. And this is also not about propagation, velocity, and time shifts. Time shifts are calculated and corrected for during seismic processing. And in seismic reservoir characterization and inversion, we assume that all the events have been aligned throughout all the volumes of data. And time shifts and velocities can be used to control the ultra-low frequencies in the inversion if you wish to do so. But this is about seismic reflectivity inversion. It's about converting seismic reflections to elastic layer properties, being able to calibrate to well control, being able to test and correct for wavelet variability, and delivering quantitative measures of reservoir properties. So that's what this is about. And so this is an overview, just 2 points I would like to make. It's talk about the method and verify the data which is proposed in verify the method by looking at some data. So first the method, and to explain what we are doing, I'd like to go back to 1999, and that was at an SEG in New Orleans when Pat Connolly first brought forward his new ideas on elastic impedance. And in fact, it was a brilliant idea he had, because he only had post-stack inversion, and he wanted to use it on far offset stacks, on pre-stack data. So to do that, he made an acoustic impedance equivalent for the far stack, and he called that elastic impedance. So with elastic impedance, he didn't need to do the simultaneous inversion we do now in the industry. He just could do his post-stack inversion on the near, mid, and far stack and get his elastic impedances. So we use that. You can use that in well tying, in wavelet estimation, and in the inversion. Now, why am I saying this is Pat had a solution to using post-stack inversion, pre-stack environment. And what I'm going to propose to you in this presentation is a method to use pre-stack inversion in anisotropic conditions. So isotropic pre-stack inversion in anisotropic conditions. And if we're talking about anisotropy, pre-stack seismic reflectivity data can at best resolve 3 parameters: VP, VS, or density, and or combinations of that. And even density is hard to get as an independent parameter from seismic data. So adding the azimuthal dimension resolves for anisotropy and azimuth, so you can get 5 parameters from your seismic data. But if you take the Ruger approach, which is the simple way of getting to polar anisotropy or azimuthal anisotropy, you need at least 5 parameters for polar anisotropy and 7 parameters for azimuthal anisotropy, which means this problem is highly non-unique. And the way this is resolved in the industry is to reduce the parameter space by assuming some background model. We can think of several background model in the industry. There's linear slip theory, Hudson model, that kind of thing. And what that does is it reduces the dimensionality of your solution space, so it becomes better resolved, and at the same time it also forces your model on your outcome of your data. So if your model doesn't, if your real world doesn't follow those models, you're probably biasing your results. So the proposed solution we have here is that we rewrite the problem so we can use isotropic modeling and isotropic inversion in an anisotropic environment. For polar anisotropy, this is the Ruger equation, and Ruger writes his equations in three terms: an intercept, a gradient, and a curvature term. So the gradient is the function of sine square theta, where theta is the angle of incidence, and curvature is the sine square theta tangent square theta, where theta again is the angle of incidence. So what you see here is the anisotropic equation for polar anisotropy, and there are two terms in here which are the Thomson parameters, the delta and the epsilon, and the delta and the epsilon typically for anisotropic environments are in the order of 10–20%, and the contrasts you see there, the VP contrast and the other contrast you see here, those are in seismic data typically between 1 and 10%. So the anisotropy has a large influence on the reflectivity, and the influence can be larger than the isotropic reflectivity itself. So not taking care of anisotropy in an anisotropic environment will bias your estimates of your inversion parameters. This is what we do to circumvent that problem. We rewrite the Thomson parameters into Thomson reflectivity parameters, so the epsilon r and delta r, and this allows us to rewrite the isotropic parameters Vp rho and Vs into their anisotropic equivalents Vp prime, rho prime, and Vs prime. And to show that this works, I have a little graph on the right-hand side here where you see reflectivity as a function of angle. And there are three curves in there. There's the dashed curve where we've used the isotropic elastic parameters and isotropic modeling. There's the solid black curve where we've used anisotropic modeling and the full Zoprich anisotropic modeling. And the dotted curve is where we've used isotropic modeling and our modified anisotropic parameters. So you see that the dotted curve is a very good approximation of the solid curve, and we can use isotropic modeling with these modified parameters to mimic the anisotropic behavior of the reflectivity. It's an example of a project we did quite a long time ago. It's on the West Nile Delta, and here we had very long offset data, and the client was after density. So the density can tell the difference between commercial and non-commercial gas. So they wanted to get density out of their inversions. And what you see here are two sets of results, just a section through your data where you see the P, impedance, VP, Vs, and density. And the top row is where we've used isotropic modeling, and the bottom row is where we've used the anisotropic elastic parameters throughout the workflow. And what you see is that the P impedance doesn't change, VP, Vs changes slightly, and the density changes completely. So the density has a very strong effect from the anisotropy. So if you wouldn't take anisotropy into account, your density estimates would be biased. So that's for VTI anisotropy, and in VTI anisotropy is usually a nuisance. You want to get rid of it, you want to circumvent it. But in HTI, that's where you're going to try and characterize fractures and cracks and stress with your anisotropy. That's where anisotropy becomes part of your reservoir characterization, and it's very important to get that right. Again, Ruger wrote his equations as a function of intercept, gradient, and curvature, also for HTI. And now, of course, the terms, or these terms R0 to R4, are quite a bit more complicated because you're talking about azimuthal data, so you have the azimuthal angle in there. So what we can do with our HTI workflow is we start with a supergathers. That's the seismic, which is both oriented in azimuth and in angle. We can do our usual isotropic rock trace inversion. That's with wavelet estimation and earth modeling and all that. Then we can invert we can look at the inverted elastic parameters, which are analyzed by what we call a elastic volume evaluator, and that gives us anisotropy information. So what comes out of the elastic volume evaluator are Fourier components, so the zero frequency, azimuthal frequencies of Fourier components, the second and the fourth azimuthal Fourier component, and the angle of the anisotropy. So we can estimate the orientation of the anisotropy from the inversion. So we can now verify the data, because what we're going to do is we're going to look at 3 ways to model our data. We're going to start with a single trace model, simple model, where you see the VP, VS, and density in the first 3 panels, and Thomson, epsilon, delta, and gamma in the last 3 panels. And here you see 2 curves on the elastic parameters. The black curve is the isotropic elastic parameter, and the red curve is the anisotropic equivalent, which we'll be using in the isotropic modeling to get the anisotropic synthetics. And to note is that, for instance, if you look at the density, there are some areas in here where the density of the isotropic model has a certain polarity, and the polarity is actually reversed by the anisotropic conditions. So then we can do forward modeling with this. There are 3 ways in which we can do forward modeling in the workbench. We can look at well-log synthetics using isotropic logs, or the anisotropic logs from the previous slide. We can look at synthetic modeling package using the anisotropic logs from the previous slide, and we can also calculate the anisotropic synthetics from the same modeling package where it uses the isotropic logs and the Thomson parameters. And this is a gather where you can, on the left-hand side, you start with low angle, so it's 0. Angle 0, and at the right hand side it's around about 60-degree angle and every 2 degrees. And what you see for this reasonably complex model, this is not one single interface but quite a few interfaces. All 3 methods, they give the same approximately the same answer, which is a good verification that the model of our theory actually works. So this is the end of the first presentation, where I talked about the method, and this is a follow-up presentation. Will give some examples of which we've used on synthetic and on real data. Thank you very much.